Alright, welcome. In this video, we're going to look at transformations of functions. And today we're going to be doing all the types of transformations that we're going to be responsible for in this class. We're going to look at translations that are vertical and horizontal, we're going to look at dilations that are vertical and horizontal, and we're also going to do some reflections. And we will solve problems related to multiple transforms. So we're going to start with the ones that we've already done, and I'm going to go pretty fast through these because we've talked about these, I think, more than once at this point. Okay, so consider this function f of x equals 1 over x squared plus 1. This is kind of an interesting graph. I don't know that we've looked at it in this class. It doesn't have any vertical asymptotes because the denominator is never 0. It's got a horizontal asymptote, y equals 0. It is going to have symmetry across the y-axis, which is something we're going to be interested in the next unit. But if we were looking at g of x equals f of x minus 1 on the outside, we know that's going to shift down 1 unit. So I'm going to say transform f to g, that's translate down 1. Okay, so I can think about, what's really special about the graph of f is that point up at the top, that local maximum, which I guess we could also call a global maximum. I'm going to just kind of label that there with a red dot, and say that's going to get shifted down 1 unit. So instead of being at 0, 1, that's going to be at the point 0, 0. And then the rest of the graph is also going to get shifted down by 1 unit. So instead of having a horizontal asymptote y equals 0, it'll have a horizontal asymptote y equals negative 1. So I can draw in the left half and then the right half also, and then get yourselves a pretty good sketch. Okay, it's not going to be as good as the professionally produced one up above, but that'll do. Now, if I want to write an explicit formula for g, okay, remember, well, g of x is equal to f of x, then subtract 1. So, and I've got a formula for f of x is the fraction, so I just copy that. I'm going to throw some parentheses on it for emphasis, but that's going to be an explicit formula for g. Okay. And if I'm confronted with h of x equals f of x minus 1 on the inside, that's going to be a translation. Subtracting 1 on the inside, that's shifting right 1 unit. Okay, and so I can do that to the graph. Think about that maximum is going to, instead of being at the point 0, 1, it'll be at the point 1, 1. It'll have been shifted to the right by 1. And then the curve will also have been shifted to the right by 1. So I can draw in the left half and the right half and have myself a pretty decent sketch. If I'm trying to write an explicit formula for h, well, I'll just remind myself h of x is f of x minus 1. Wherever I see x in the formula for f, I'm going to replace it with x minus 1 in parentheses. And so I'll say that's 1 over x minus 1 squared, then add 1 on the outside. So to summarize our translations, I might say that if k is a positive number and I want to take a graph of f of x and I want to shift it up k units, I'm going to add k on the outside. If I want to shift down k units, I'm going to subtract k on the outside. Okay, if I'm going to be shifting left and right, that's going to be, adding or subtracting on the inside. So if I'm going to the left, I'm going to be replacing x with x plus k in parentheses, and adding k on the inside, and shifting to the right is going to be subtracting k on the inside, taking the formula for f and replacing it with x minus k in parentheses. All right, now we're going to talk about some dilations, and we're going to start with the vertical dilations, which we've already done in this class, and so I'm going to go pretty fast through those. So, in the case of g of x equals 1 half f of x, we know that's going to be multiplication on the outside is a vertical dilation by a factor of 1 half. Okay, so we're going to think about that maximum, and we're going to say, all right, instead of being at 0, 1, it's going to be 0, 1 half, because everything's half as high as it used to be. And then the graph otherwise will be, squashed vertically, okay, dilated by a factor of 1 half, and so we get that. And if we want to write an explicit formula for g, okay, well, g is half of x, which is like 1 half multiplied by f of x on the outside. And so I'm going to say that's 1 half multiplied by that fraction that defines f on the outside. And, if I did need to, recognize an equivalent form of that, say in multiple choice or something, I could distribute the 2 over the x squared and the positive 1. I could recognize that that's the same as 1 over 2x squared plus 2. Now we're going to look at the horizontal dilations. So h of x is going to be f of 2 times x. So multiplication on the inside, multiplication is a dilation, and on the inside is horizontal, so this is it. We're talking finally about horizontal dilations in this class. And that's why I got this graph here, that you could actually see something happening to it if you horizontally dilated it. It wouldn't necessarily affect it vertically. So h of x is going to equal f of 2 times x. We want to sketch the graph of y equals h of x. Okay. Well, I think what I'm going to do, I'm going to go back up to the original graph and just point out a couple of points that are on this graph. Okay, so I'm going to point out that f of 0 is equal to 1. And I'm also going to say f of 1. I'll label this point in blue. I'll say f of 1 equals 1/2. See that off the graph, and you can also see it from the formula. F of negative 1 is also going to equal positive 1/2, and that makes a lot of sense if you think about plugging in negative 1 for x in the formula. Okay, and so I've got these 3 points here. All right, so I brought this thing over with us for us to refer back to when we go and think about h of x. Okay, so I'm going to start with h of 0. Okay, and right in here, all right, h of 0, well, that's going to equal f of 2 times 0. And that's just 2 times 0 is 0, so that's equal to f of 0, which we already knew on the graph was equal to 1. Okay, so that point's going to be unchanged at 0, 1. But then I'm going to think about what is the value of h of positive 1. I'm going to run out of room here. I realized I was covering up more than I needed. So if I take the value of h of 1, that's going to equal f of 2 multiplied by 1. And that's going to equal f of 2, which, I mean, I suppose we could figure out, but that isn't one of the points that I had, labeled. Okay, so that's probably not going to be the best, place for me to draw. I need to think about what x value can I plug into h to get f of 1 and get f of negative 1. And so that's going to be x equals 1/2 and x equals negative 1/2. So if I plug in x equals positive 1/2 to h, I'll be taking f of 2 times 1/2, which is f of 1, and that is 1/2. So that's a point I know. If I plug in that x equals negative 1/2, I'm going to get f of 2 times negative 1/2, which is going to be f of negative 1, and we already know that was equal to 1/2, so I'm going to have this point right over here at negative 1/2, 1/2. And we can see that the graph of f has been kind of crunched. It's been horizontally dilated by a factor of half, right? It's closer to the y-axis than it was. So it's just gonna all happen twice as fast. That was not good. That took too long for that. And that should be good. Okay. And I think you can see from the original to the new one, the transform, that's going to be horizontal dilation by a factor of 1/2. And then the reason why, we had f of 2x and it was horizontal dilation by a factor of 1/2, it goes back to the idea right down here in the writing in blue, where I had to think about what x values I could double to get back to points I knew on the graph of f. That was kind of why it was like a backwards operation, because I was having to do that backwards line of thinking. What x do I plug in to get this? So in summary, if we are, dilating a graph by a factor of k, if it's vertical, it's going to be multiplication on the outside, so I'm going to multiply k times f of x. And if it's horizontal, it's going to be on the inside, but we saw that it was the opposite of what we expected. It was f of 1 over k multiplied by x. So if I want to horizontally dilate by a factor of 2, I'm going to be taking f of 1/2 x. Whereas if I want to dilate by a factor of 1/3 horizontally, I'll be taking f of 3 times x. And then I might add on that we can kind of like summarize all of our transforms by saying like any kind of inside impact on f is going to be a horizontal movement, and any outside impact is going to be a vertical movement, and adding corresponds to translation, and whereas multiplying corresponds to dilation. Where do I looks like I forgot to write an explicit formula for h, and this is something that we need to be able to do. So I'm just going to go in and say, all right, h of, no, not h of 2x, h of regular x equals f of 2x. So wherever I see x in the formula for f, I'm going to replace it with 2x in parentheses, and that's going to end up being the same as 1 over 4x squared plus 1. Okay, I think that's going to be enough for that example. All right, now we're going to talk about some reflections. So if g is the function, oh wait, I think it's supposed to be an a. Okay, a is supposed to be the function defined by a of x is the negative of f of x, and we want to sketch the graph of a. Okay, well that's just going to be a reflection across the x-axis. We've multiplied the function by -1 before in this class. Okay, everything became negative. All the outputs became negative. So we're going to say we will reflect across the x-axis And so that's just going to take that point up here and cause it to go to y equals -1 and the graph to just go upside down. If we want to write an explicit formula for a, well, a of x is going to equal negative of f of x. So that's like -1 multiplied by f of x. And if we wanted to write this just as one fraction, we could put the negative on the top. We could also put the negative on the bottom. I guess we could say it's +1 over -x squared minus 1. But what we can't do is put it on both, right? Because if we had negative over negative, well, that would just be like multiplying by -1 over -1, which is actually multiplying by 1. Okay, not -1. So that's a reflection across the x-axis. All right, if we think about b of x is f of -x, this is going to be a reflection across the y-axis. But if you think about it, this thing, it already has symmetry across the y-axis, so if I reflect it across the y-axis, nothing's really going to happen. But if we write an explicit formula for b, we know that b is f of -x, so wherever I see x in the formula for f, I'm going to replace it with -x in parentheses. You can see why that happens, right? Because that -x is going to get squared, and that's -1 times x times -1 times x, and -1 times -1 is +1. So that comes back 1 over regular x squared plus 1. Okay, so it didn't change when I reflected across the y-axis. Okay, so to summarize, if we are going to reflect across the x-axis of vertical reflection, that's where y is going to get replaced with -y, and we're going to multiply -1 on the outside. Whereas a horizontal reflection, like a reflection across the y-axis, we're going to replace x with -x in parentheses in the formula. If you wanted to actually see a reflection across the y-axis that did something, you could consider f of x equals the cube root of x. And so, just to remind you about this graph from Algebra 2, it kind of looks like a sideways version of y equals x cubed. Which in some ways it is, because of their relationship as inverses. I would point out that it's momentarily vertical right there at the origin. That was a decent drawing. But if we considered, like, okay, so this is f of regular x equals cube root of x. Okay, if I was to go ahead and think about, okay, well, what if I did f of -x? What if I reflected this across the y-axis? Cube root of -x. Okay, we'll just reflect across the y-axis. Okay, we had it going up and to the right, so now I'm going to go up and to the left. Okay, but really leveling off. And then down and to the right instead of down and to the left. Right, reflected across the y-axis. If you look at this, this is actually also a reflection across the x-axis, and the reason for that is that, the cube root of -x is the cube root of -1 times the cube root of x. You can do that with radicals, and the cube root of -1 is -1. Okay, so that's negative of the cube root of x, which is what we would get if we had reflected across the x-axis. All right, now we're going to get into some more meaty examples. All right, so the function f has domain -3 to 3 and range 2 to 6. G is given by g of x as -3 f of x plus 2 plus 5. What are the domain and range of g? All right, so I'm going to just start with a picture of the domain and range of f. All right, so we're going to just start with this domain just like that. X is running from -3 to 3 and y is running from 2 to 6. Okay, g is -3 f of x plus 2. Well, I'm going to start from the inside and work my way out. F of x plus 2 shifts left 2. So that's just going to impact the x values. The y values will be unchanged. I'll just move to the left by 2. And then I'm going to have the next transform is, okay, multiply by -3. So I'm going to say vertical dilation. I'm not going to write out by a factor of -3, but I can do that. So, the output values are going to get multiplied by -3. So, 6 to -18 and 2 to -6. Okay, but that becomes negative, so I'm going to label these as -6 and -18. Just going to run out of room. Okay, then I'm going to move up 5 units. Okay, and then that'll be the last one. I'm not sure if that's going to fit. Okay, yeah, we'll probably need a arrow after that because I already hit my last transform. And this is going to give me my final domain of range. So add 5 to the y coordinates to go up 5. So -1 to -13 and -5 to 1. So I'm going to say the domain and range of g. Domain of g is going to be -5 to 1. And the range of g is going to be -13 to -1. All right, now the next problem, this is another multiple transform problem, and these can be particularly tricky. Okay, so I just am gonna try to suggest that we, go step by step. Actually, I skipped ahead, but that was what I was doing in the notes, and I actually went in and kind of like replaced or switched the order of the examples. So that when I recorded, I would go in the right order. Yeah, I liked this one best. So we're going to start off with function f, and we don't really have a formula for it, but we're just going to do some transforms for it. So the first is going to be dilating vertically by a factor of 7. Then the second transform is going to be horizontally dilating by a factor of 11. Then after that, we're going to translate the result down 4 units, and then write 12 units. So I'm just going to start with f of x right here in black. And then I'm going to say, all right, the next step would be red, vertical dilation by a factor of 7, multiply by 7 on the outside. Okay. Then horizontally dilate by a factor of 11. Okay, well, okay, then after that, I think I'm going to, replace x with 1/11 of x in parentheses. Okay, well, that extra set of parentheses didn't really do anything, so I'm going to actually get rid of them. Okay. Then, after that, we're going to translate the result down by 4 units. That will entail subtracting 4 on the outside, so 7f of 1/11 of x. Then subtract 4. And then lastly, we're going to go right 12 units. And that's going to involve replacing x with x minus 12 in parentheses. And so then that's, after all those transforms, that's going to give us a formula for g of x in terms of f. So 7f of 1/11 of x minus 12 minus 4. And there we go. That was a lot of transforms. That was, 4 of them. Okay, this next problem here is pretty much the same idea, just in reverse. But this one can be particularly tricky because the order of the transforms does matter. So I want you to think about, just starting with f of x, and then what am I going to need to do to get this formula right here? G of x equals f of 5 times x minus 6. So you might think, okay, start by replacing x with x minus 6 in parentheses because that's what you can see. But I'm going to tell you that's not going to work for us. Okay, that's not going to be the correct order of transform. And I'll go ahead and show you why off to the side. But first, I'm going to replace x with 5x. So that is going to be a horizontal dilation by a factor of 1/5. And I'm going to write that off to the side. Okay. Then after that, I'm going to replace x with x minus 6 in parentheses. Then it'll look exactly right. So if I replace this x with x minus 6, then that will represent a shift right by 6. And I'm realizing I probably could have used a little bit of color to emphasize that I was, replacing x with 5x, and then I was taking that x and replacing it with x minus 6 in parentheses. So this is going to be a horizontal dilation by a factor of 1/5, and then a shift right by 6. And the order does matter, right? And I'll show you that off to the side. And I would not recommend writing this down on your paper because this is like wrong work. So if I had done like first replace x with x minus 6 and then replaced x with 5x after that, I'd have f of 5x minus 6. And that's clearly not what I've got up there. Okay, what I've got up there is exactly the same as this thing. And so, that's, what would have happened had I, gone right 6 and then horizontally dilated by a factor of 1/5. But I don't want to spend too much time with that on the screen because I don't want you to, get the wrong impression there. All right, I really like this next one here. The piecewise linear function f defined on the closed interval -3 to 4 is shown in the graph. The function g is given by g of x equals x plus 1. Sketch the graph of y equals f of g of x. So I need to kind of get in there and think about, okay, what is y equals f of g of x even talking about? Well, g of x is x plus 1. So f of g of x, wherever I see x in the formula for f, I'm going to replace it with x plus 1. Or I guess that wouldn't really be relevant in this case because I don't have a formula for f. But I'm just going to say, all right, g of x is x plus 1, so I'm really taking f of x plus 1. And when we see that, that needs to activate in our mind, okay, we're going to be shifting left 1 unit. And this kind of L-shaped graph, this will be really easy to shift left by 1. Or in a multiple choice setting, would be easy to choose out the correct one that had shifted the graph just left by 1. And then there you go. I've shifted the graph left by 1, got myself a really good image, and I'm happy. All right, now this next one, this is kind of a lot. And I am just before at the outset, before I even start in on this problem, I'm going to say, like, I recognize there's probably a different way to do this where you kind of just track the movement through just start with -3 and do all the transforms to it. I'm a little iffy on that, and I'm sure you are as well. So what I'm going to do, I'm going to try to find the values of A and B and C. Okay, so the graph of G is constructed by applying 3 transformations to the graph of F in this order. Horizontal dilation by a factor of 3. That means B equals 1/3. A vertical dilation by a factor of 4, so that's going to be A equals 4. And a translation vertically by -4, that means C equals -4. So G of X is equaling 4 F of 1/3 X plus -4, so I might just call that -4. Okay, as a result, if I'm taking G of, -3, I'm going to be interested in f of -1, I think. Okay, so I'm going to say over here, all right, g of -3 equals 4 times f of 1/3 of -3 is -1 minus 4. So it's going to be 4 times f of -1 is 6. So that's 4 times 6 is 24 minus 4, and that's going to equal 20. All right, now this next one has got 1, 2, 3, 4 line segments in a semicircle. All right, give a sketch of the transformed graph for y equals f of x minus 3 plus 2. All right, so that's going to be shifting right by 3 and then up by 2. All right, so what I'm going to do, I think I'm just going to try to, you don't probably have this luxury if you're working on, a piece of paper. Oh, whoops, I somehow messed that up. I'm going to just color over this thing so I have a good sketch of it. And then I'm going to select the whole thing, and I'm going to go over here and drag it off to the side and say, all right, I'm going to shift right by 3 and up by 2. All right, so this had kind of a y-coordinate of -2. So if I go up by 2, the y-axis is going to kind of sit tangent to the bottom. I mean, the x-axis is going to sit tangent to the bottom of that circle. So I'm going to go over here. I'm going to draw in a horizontal line. That didn't quite go as well as I'd hoped. I'm going to try that. That really didn't. Okay, that ended up being perfect. Okay, I think somehow it's kind of smart. And if I go right by 3, well, then the original far left spot of -3 right there, okay, that will become x equals 0, which is going to be the y-axis. I'm going to draw in a vertical line through that point, and hopefully it'll be real smart. Yeah, there we go. And here I have got myself a really good sketch. All right, so what would that be from -2 up to +2? So that would be y equals 4. Yeah, because we went up by 2. Went from, oh, whoops, I'm still doing on the automatic shape drawer. And then I shifted right by 3, so this would be at x equals 5. I think that's plenty of scale. Oh, I'm kind of gone off my field I can write on, but that's going to be x and y, and that's a really good sketch for us. All right, 2 more examples. So the function f is given by f of x equals x to the 3 plus 3, and g is going to be x to the 3 divided by 8 plus 3. And the question is, all right, which of these describes a transformation of the graph of f that gives the graph of g. Okay, and they want you to choose answer choice B, right? They really want you to say, oh, I multiplied by 1/8, that's going to be a vertical dilation by a factor of 1/8. And that is not the answer, right? Because a vertical dilation by a factor of 8, I'm going to actually go through and say, all right, that would be 8 times f of x, which would be 8 times x to the third plus 3. And that's going to be 8x cubed plus 24, which is definitely not what we're seeing over there. Okay, a vertical dilation by a factor of 1/8. Okay, same thing. Multiply the whole thing by 1/8. And that's why this one isn't going to work, because I would need to, not the squared x cubed, is that I would need to multiply the x cubed by 1/8. But I would also need to multiply the 3 by 1/8 in order for it to be a vertical dilation by a factor of 1/8. Okay, horizontal dilation by a factor of 1/2. That's replacing x with not 1/2 x, but 2x, right? Because it works the opposite of the way we expect. So that would be, okay, 2x taken to the third power and then add 3. Replace x with 2x in parentheses. Now if I take 2x to the third power, that would be 3 2's and 3 x's. So that would be 8x to the 3 plus 3. That's still not what we have. All right. Horizontal dilation by a factor of 2. That would be replacing x with 1/2 of x in parentheses. 1/2 x taken to the third power and then adding 3. That would be 1/8 of x to the 3 plus 3. Wait a second, that's exactly what I've got. That's going to be answer choice D. Okay, horizontal dilation by a factor of 8, it'd be kind of like C, but even farther off. It'd be like 8 to the third, whatever that is, and some big number. We don't really want to do that. Now, the last example I've got for you is here's a table. And you've got these two functions f and g. The pattern of the values of f and g continue, repeating every interval of width 4 for x between 0 and 32. The graph of the function g is the result of a sequence of dilations of the graph of the function f. We're going to find the dilations. Right, so I think on this one, this is a very tricky question. And we struggled to replicate it in a way that wasn't showing you the exact same one. So you see that f goes 0, 5, 10, 5, 0. 0, 5, 10, 5, 0. And it's going to keep doing that all the way out to 32. So it's going to kind of keep going up and down and up and down and up and down. G seems to go 0 to 40. Okay, so to me, it looks like that's either going to be a vertical dilation by a factor of 4 or maybe a vertical dilation by a factor of 8, but I'm not really sure. So I think what we need to do is think about the zeros. So maybe I'll also write out kind of a skeleton formula. That g of x is obtained by dilating the graph of f. Say a times f of bx. Okay? And then I think about two that are the same. Think about maybe the zeros. So the zeros are happening every 2 on the graph of g, whereas they're happening every 4 on the graph of f. So if they're happening twice as often, I feel like b should be 2. But I'm not really, this is kind of just a hypothesis, but b equals 2. So what if g of x equaled a times f of 2x? And we could try some numbers and see how this goes. All right, we could say, let's say, what is g of 2 equal to a times f of, 4? Yes, that's true. These are all related. And I could say, yeah, g of 0 is related to f of 0 by some multiple. But the fact that they're all zeros, that isn't really helping me. Okay, so that does seem reasonable. But what about g of 1? G of 1 is going to be a times f of 2 times 1. Okay. And, okay, well, that's possible because f of 2 is 10. Okay, so g of 1 is 40 equaling some number times f of 2 was 10, and then a is 4. Okay, so that's my new hypothesis. My new hypothesis is g of x is 4 times f of 2x. Okay, and then I could go over here, and I'm just going to try another value, like maybe g of 5. That's probably a bad idea. How about g of 3? Is that going to be is that going to be equal to 4 times f of 6? F of 6 was 10. Yeah, this is working. And you can go back in, you can see this is going to work for all of them. So I'm going to conclude that G is formed by vertically dilating by a factor of 4, and then a horizontal dilation by a factor of half. Okay, because I'd replaced x with 2x. That was work the opposite way we expect. All right, so that's the last example for these notes. So that's going to be all for this video. Thanks for watching.